Okay, that's on. So welcome everyone. We got Jordi and Pau from Vocdoni, and they will be talking about DAVINCI, which is the newest voting protocol. We'll be walking through their mission, why they think digital voting and secure voting is important, some of the success stories, the use cases, and how the protocol works. So I'll hand it off to Jordi and Pau to get started.
Okay, yeah, thank you so much. Thank you, everyone, for joining us. Yeah, let me share the screen so we can have some slides. Let me check if I can do it. Okay. Now, let me pin. Yeah, it's already pinned, right? Okay. Okay, can you see the screen? Yeah. Sorry, I cannot hear you. Yeah, you can see the screen, right? I'm sharing.
Yes.
Okay, perfect.
Sorry about that.
Sure, perfect. No problem. Thank you so much. Okay, let's go. So yeah, I'm Jordi. I'm working at Vocdoni since some years ago, and yeah, today in this learn and share video from PSA, I would like to introduce DAVINCI, which is like the latest protocol we have been working on at Vocdoni. I will do a brief introduction of what is Vocdoni, some use cases that we had, and we'll pass the micro to Pau to explain more technical details of DAVINCI. So yeah, let's start. Okay, so what is Vocdoni? Vocdoni is written in Esperanto, and it means to give voice. And it's an open source digital voting project that leverages distributed technologies and cryptography to deliver secure and transparent decision-making processes. So our vision is to improve democratic health and promote participatory governance using decentralized and open source technology. From that vision, we end up with a mission to build a censorship-resistant, secure, and transparent voting protocol that facilitates decision-making for communities and organizations. And we are organized around the values of digital sovereignty, open source, public goods, and for using the tech for good. So I would like also to give you some insights of our mindset, of the foundations of the mindset that define us. So our end goal is to provide a voting system with all the guarantees that a democratic voting process must have. We also focus on practicality. We cannot expect that people understand Web3 or technology at all. So all technical aspects must be transparent for the end user. And yeah, we also are privacy first. We think that voting system should be censorship resistant, should be end-to-end verifiable, accessible by anyone, anywhere, at any time. And yeah, we also would like to provide turnkey solutions. So you have the protocol, you have the an API and an SDK for interacting with the protocol. And on top of that, you have a UI that will be what the end user will have. So when I talk about all the guarantees that the democratic voting process must have, there are certain attributes that must be accomplished by any digital voting system that can be considered secure and transparent. Before talking about these properties, let me also give a bit of the background that we have and where we came from. So Vocdoni as a project was born in 2018. It was led by a multidisciplinary group of pro-democracy activists. And it was in a context of state repression against the Catalan civil society for running a democratic referendum about self-determination. And at that point, we realized that current usable voting solutions are opaque, are costly, and are centralized. And that the world needs an unstoppable voting system, because nowadays voting is an exclusive asset controlled by nation states. If you try to imagine how to create a voting at your home, at your municipality, at your country, first you don't have the census, then it's an exclusive asset because you need a lot of money to organize it. And we want to change this paradigm with Vocdoni. So going back to what a proper democratic voting system should have, we have some properties that are kind of agreed between the community that is working in this field. So we have three groups. We have security properties, integrity properties, and verifiability properties. Going a bit more in depth of each one, in the security properties, we have the ballot privacy. So no outside observer can determine the contents of a specific vote. Then we have the receipt freeness. So after an election, a voter cannot prove how they voted. And we have coercion resistance. So meaning that during an election, a voter cannot prove their vote to a coercer. Then if we go to integrity properties, we have censorship resistant, meaning that no party, even the administrator of an election, can censor a valid vote. We have non-repudiation, meaning that no party can modify or erase a vote that has already been cast, with the exception of a valid voter nullifying their past vote and willing to cast a new vote. So it would be like a vote overwrite. Then we have also the correct execution. So no party can forge a false tally of the casted votes. And finally, in the third group, we have the verifiability properties. So we have, it's all of them together. It's what we call end-to-end verifiability. So having like individual verifiability, meaning that a voter can verify that their ballot was correctly contained in a set of published results. We have the universal verifiability, meaning that anyone can verify that the published results correspond with a set of published votes. And we have the eligibility verifiability. So anyone can verify that each vote included in the results was cast by an eligible voter. So it was in the census. And that each voter casted no more than one vote. So if we put together these three properties, the individual verifiability, the universal verifiability, and the eligibility verifiability, we have what we call the end-to-end verifiability on a voting process. So having that in mind, during the past years, we have been providing organizations, institutions, and any human group with voting technology that can be used and it's easy to use. And I wanted to highlight some use cases that we have. So these use cases will be will be grouped by the verticals that we identified on the market. But before going a bit deeper on the use cases, I want to also highlight the tech evolution that we have. We have been always trying to innovate and to use the best solutions that we had in that moment for solving like real world use cases. Sorry. So when we started in 2018, it was Q1, Q2 of 2018. We forked Zcash to try to create an MVP to show the feasibility of blockchain voting, and by using cryptography and distributed technologies. So we had a real use case with 28,000 votes, and people did not realize that they were using blockchain technology. And this was in 2018, some years ago. The problem is that solution is that it was limited and it lacked of programmability. Then in another iteration, in the second part of 2018, we tried to build a custom Ethereum Proof Authority network, but at that point, Ethereum was missing the cryptographic primitives for building a private and anonymous voting system, and we also had an scalability problem. And because of that, on 2019, we decided to build a custom L1 blockchain based on Tendermint BFT. Nowadays, it's called Comet BFT. And we were using Zerocom on the client side for generating all the zero knowledge proof that our anonymity and privacy are based on. This custom blockchain is still running. This is the blockchain that we are using right now while we are developing the new protocol, implementing the new protocol. And it's being used by more than 200 organizations, and we also have more than 200,000 votes processed. And then we end up in 2024, where we thought that the technology was ready for trying to implement what we think is kind of the holy grail for digital voting. And it's the project, or the code name was DAVINCI. and we leverage full zk-SNARK voting state machine. Why we are doing this? It's because the custom tendering blockchain, from our point of view, it is not like decentralized enough for holding national state voting, and we don't solve the problem of collusion. Okay, so going back to the case studies I was mentioning, I would like to highlight that we have a proven track record of delivering secure and decentralized voting solution across both the Web 2 and Web 3 markets. So I'm gonna go for each vertical. So, for example, using this unstoppable voting technology, we were able to provide the Belarusian opposition that were in the need of anonymous, censorship-resistant, and tamper-proof voting technology for their citizen council elections. So, in an environment of censorship, political pressure, people in fear, they decided to integrate the Bogdani protocol via the SDK that we provide to their own app. And it was super nice because more than 6,000 people casted their vote under a repressive scenario, sorry. And we had also international observation mission that verified that all the process had the democratic guarantees that they need to have. We provide also a voting solution to political parties. For example, we have the success story of Esquerra Republicana, which is one of the largest political parties in Spain. And it was super nice because the vote was decisive for electing the Catalan's presidency and also for the formation of the Spanish government. They had a really high turnout. And as you will see, like in the different use cases that we had, the voters authentication is a super flexible mechanism. So it's up to the organizer of the election to choose their preferred authentication mechanism. In this case, Esquerra Republicana were using an email with a unique access code that were received as a two-factor authentication. And we are very happy because they're still using it for their higher stake internal voting processes. Okay, then we also provided some solutions to governments. We have the success story of the Barcelona City Hall. In this case, the Barcelona City Hall is using Decidim, which is one of the biggest governance solution, open source governance solution. Decidim is used in the Barcelona City Hall, but also in the City Hall of Paris, New York. It's being tried to be used by the Brazilian government, and we are very happy that they decided to use Bogdani and to integrate Bogdani in their governance solutions. And also we have the municipality of Bellpuig, that it was the first full digital referendum that was held under the Spanish law under COVID restrictions. So people had the chance to vote digitally from their home, but we also provide like a physical space, a secure physical space for people that doesn't understand that much about technology to go there and to vote with a QR code and some other credentials that you can see here in the photo. Then we also provide solutions to global organizations. In this case, it was the Football Club Barcelona. It was for the advisory council of the Football Club Barcelona, and given that their members are spread around the world, we provide this digital voting solution where the members could be identified using member ID and also a two-factor authentication. In that use case, we were very happy because most of the members were over the age of 60. So it's super cool to see, like, I'm not going to say all people, but I mean, people that maybe is not that much into technology to use flawlessly the solutions and the voting project that we implemented for them. We also, in terms of scalability, we also provide our voting technology to Omnium Cultural, which is the largest cultural organization in Europe. It was also under repression environment. So Omnium is let's say a pro-independence Catalan organization. So they needed the censorship-resistant properties and to be really sure that no any of the votes or the tally were altered afterwards the election. Yeah, we also had nice polling during the Catalan parliamentary elections. The cool thing, or the thing to highlight about this case, is that we decided to authenticate people using state-issued digital certificates. In that case, was something called ID card. This is a digital certificate that any person in Catalonia can have. And yeah, it was super nice. We had a lot of media coverage, more than 1 million views in national TV. And it was a really nice experiment that highlighted that the voting technology is ready for being used, and it's convenient, it's cheaper, and it's more gives you more pleasure to use than spend all the day like outside your home voting and going to the polling station and so on. And yeah, one of the use cases that we cover the most is for professional bodies. In this case, it was for the Official College of Nurses of Barcelona. And yeah, they had more than 40,000 members. And yeah, again, we use their own credentials to authenticate, and then we enabled that two-factor authentication via SMS and email for having this extra layer of security. And yeah, we are very happy that these professional bodies are among the most interested user groups on using digital voting, because there's something they need to do. They are forced to do it each year. And finally, we also provide the technology to DAOs, and we facilitate on-chain decisions. This was an endeavor we end up having in Farcaster. I don't know if you're familiar with, I don't know if you're familiar with this thing about the frames and the mini apps and so on. So basically what we did was to integrate a way to create voting processes from the application and to make people be able to vote from their social feeds. And it was super nice. We had good feedback on them. And yeah, and for example, the Degen DAO, which is one of the, I would say, one of the biggest DAOs in the Farcaster space, is using this solution for their voting needs. So yeah, as you can see, we have we had like a lot of different use cases, and this validates the need of the market and of the people to use this kind of technology. It's just better to use this technology. We are working online all the day. All the financial structure is online, but we're still voting like 200 years ago. So I think it's time to change this. And now we think that the technology is ready. So yeah, this was a bit of a background about Bogdoni, where we came from, who we are, some use cases. And now, if you don't mind, I will pass the micro to Pau, so he can introduce you to DAVINCI and the new protocol we are building. I'm gonna stop sharing the screen so Pau can share his screen. And meanwhile, I will be listening and preparing the live demo with the wallets you are sharing on the chat. Thank you so much.
Thank you, Jordi. So, hey, I'm Pau. I am current tech lead at Bogdoni. I've been also a founder of Bogdoni together with more people in 2018. So I have been some time already on this field. And yeah, now I would like to introduce the technical side and the details of the new protocol we're working on, which is the DAVINCI protocol. I hope I'm gonna be a bit technical here. I hope I'm not getting people bored. Yeah, let's try to make it quick, fast, and and clear for everyone. So, and yeah, a last disclaimer: I'm not a cryptographer. I am a computer engineer with some cryptography knowledge, but yeah, we have a cryptographer in our team. So if there are very specific questions on cryptography, I think I would like to forward to her. So DAVINCI is an acronym that means decentralized autonomous vote integrity network with cryptographic inference. Here you have the white paper URL. So if some of you want to open it, you can also have some extra details on this document. It's whitepaper.bogdoni.io. So let's start explaining why the acronym, why the name, because it means a lot actually. So first is decentralized autonomous, meaning that the protocol can run autonomously, same as a DAO, right? So this is because we're using, as you may know, Ethereum smart contracts and a specific purpose ZK rollup network. At some point we can disappear and the protocol should keep running. It's a vote integrity network, so this is the main objective of the protocol. And it's a network made out of sequencers that accumulate, verify, and aggregate votes and send the final proof to Ethereum. And it uses cryptographic inference. So meaning that in order to get conclusions, so to get the tally, the results at the end, we are only using cryptographic premises. So we try to avoid a single point of failure and trust to any authority here. Yeah, these are the design's properties. So when we started to design DaVinci, this was the list of things that we wanted to accomplish. And this comes from our experience implementing voting solutions. So for instance, I'm not gonna go through all of them, but for instance, the Ethereum signers compatibility and hardware wallets is a requirement that we have, and it's quite hard to achieve in a voting protocol like this, because as you may know, Ethereum signature scheme is not very ZK friendly. Also, there is an issue with deterministic signatures that makes it makes very hard to create nullifiers for a voting process. And also, if we want to support hardware wallet, it means that we don't have access to private keys. So we only have, some signature that it's not the perfect tool for voting. I would say like this. We also wanted to support other identity systems like RSA or ADDCA. So we created the protocol flexible to be able to plug different identity systems. Everything should be based on ZK snarks. That's also very important from the beginning to the end. Lastly, I would just say that the technology and the design is done to be implemented now. So we are not basing our solution on not ready cryptography or technology. We want to use the tools that we already have in order to have the system ready yesterday. Let's see a quick overview on the architecture. We have mainly three components here. We have the voters that send the votes. Then we have the network of sequencers that work off-chain, let's say, and they are accumulating votes from the voters. They are accumulating votes, aggregating them, adding them in a shared state, and then committing this state to Ethereum. So the only information that is stored on Ethereum is the root hash of this state. This is how the state looks. It's more or less. It's a sparse Merkle tree. It's very common in blockchains to use a Merkle tree as a state because it's a deterministic construction. And also in ZK snarks, it's very common. So we're using the ident3 implementation, the one that is available on Circom. If you have been using Circom or Snarks.js, then you probably are using the SMT processor. So we use exactly the same tree. And we have implemented these in other languages. So we have in Circom and in Go, in GNARC, and so on. And this is how it looks. This is the state for a single voting process. So on every voting process, there is a new state. In order to start a voting process, the organizer needs, let's say, to build the initial state. And from this initial state, new votes are being accumulated and added, and the state is evolving to a new state. The state contains the configuration of the voting process. This is the left side. So these are static paths where some static information is stored, like the process identifier, the census route, the ballot mode, and we will talk about that later, encryption key, and so on. So these are like things that the results are changing, but the rest are not changing. So they resume the voting process itself. They describe the voting process. And in the right side, we have the nullifiers, the ballot, the addresses, and the vote IDs. So on every new batch of votes, new of these Merkle tree leaves and paths are being added to the state. And this state is constructed by several sequencers. So it's a matter of collaborating, let's say, using Ethereum as the coordination platform. Let's go step by step how it works. So the first one is the orchestration. It means that the organizer or someone needs to create the voting process on Ethereum. We have a smart contract where you can send a transaction with some data, like the census root hash, the duration, and the ballot configuration. And then on this transaction will trigger the sequencer network to start to process votes that eligible voters are sending to the sequencers. Yeah, of course, the census needs to be built in advance. That's something which is not part of the protocol. You can build the census in many ways. So you can have a list of addresses, or you can use an NFT or ERC20 token to build also census. We have some tooling around it, which facilitates the creation of a census. It's also possible to create a ZK snark verifying that a census out of some data on Ethereum is correct. That's something we still have not started to implement, but that's something that we want to do also in the future. But for now, you need to build your census. That's organizer responsibility. Yeah, then in the step one, we have the sequencers generating the encryption key. This is a threshold encryption key, homomorphic. We're using homomorphic encryption, El-Gamal, on elliptic curve. So we have designed or elaborate a distributed key generation protocol that the sequencers must follow in order to create together this threshold encryption key. Threshold means that in order to decrypt the results at the end, you don't need the full set of sequencers. You don't need the 100%. You need maybe the 60, 70, 50%. It depends on the threshold. So they will use Ethereum, our Ethereum smart contract, to coordinate and to go through the steps in order to create this encryption key. This is around 2 transactions per sequencer, more or less, to Ethereum in order to exchange the information required for doing this MPC. Then once the key is generated, the voters can start sending ballots. And in this case, the voter needs to build a valid envelope that follows a list of constraints. And this is verified by a ZK snark, which is executed or generated on the browser of the user. The constraints are that the voter is eligible. So there is a census Merkle proof that proves that the voter is part of the census. And the ballot is correctly encrypted with the encryption public key and El-Gamal and so on. So all of this is also verified inside the ZK snark circuit. And the encrypted ballot, or let's say the plain text ballot, follows the voting rules. So if you have 4 candidates, you cannot vote to the 5th candidate, right? So we enforce all these rules on this ZK snark, which is generated on the client's device. And regarding the ballot rules, this is also important. We have designed something that we call the ballot protocol. It's a very simple mechanism to define several different kind of voting types. With this system, you can You can do range voting, rank voting, quadratic voting, budgeting, even multi-choice, and so on. And yeah, I'm not gonna go deep into this, but you have all the documentation also in the Bogdoni developer portal about this valid protocol, and also in the white paper. But mainly, as to summarize it, a valid is an array of numbers, and then you have a set of rules that decides how this valid must be formatted, and these are the valid variables. So max count, for instance, indicate how many fields of the array needs to be sent to the voting process. Yeah, then step 3, votes are batched, and here is where the sequencers get into work and committed to Ethereum. So the sequencers will fetch votes and will aggregate them. Currently, our batch is of 60 votes. We want to increase this to 100 or maybe even 1,000. We believe it's possible. As bigger the batch, bigger also the circuit. So this is a bit like the block size on Ethereum, right? If you want to have compatibility with device, with commodity hardware, then you cannot like increase a lot the size because then only people that can afford very big machines can participate in the sequencers network, and this goes against decentralization. So the votes are homomorphically added to the existing encrypted results. And also, this is very important, they are re-encrypted by the sequencer. So re-encryption, when we're talking about homomorphic encryption, means to add, to sum 0. So if you sum 0 to something which is encrypted, you're having the same result, but you're changing some, let's say, some parameters of the encryption payload that will remove any receipt that the user might use afterwards in order to prove how they vote. Sorry, I'm gonna disable notifications. Okay. Okay. So the votes are re-encrypted, and then the batch of votes of re-encrypted votes, which is everything, it's verified on inside zk snark. So all of this must be safe, and sequencers must always follow all the rules. So once the batch is aggregated, then the sequencer creates the state transition. So he proves that from one route to the next one, there is only the batch of votes added to the state. The results are correctly added to the new votes, and everything works as expected. So then we have the new state root, and this state root is sent to Ethereum, which verifies the zk smart proof. And if it's correct, it will update the state root on Ethereum. This is how any zk rollup works, to be honest. But in this case, we are doing it for votes. The sequencer network can work in parallel. That's also a nice property from our zk rollup system. Not all of the zk rollups allow this property to have a parallel.
Oops. Hey, you're muted, Pau. You went down for some seconds.
Yeah, I know. Sorry. Let's keep going. So yeah, I was saying that we allow working in parallel for the sequencers, and that's something that I would say most of the zk rollup networks around do not allow. It's that everyone can be also actually a sequencer. Everyone can prove a state transition, and everyone can send it to Ethereum. So they can work in parallel. Parallel doesn't mean that this is still the problem with the data races, right? So if there is a sequencer working on a state transition and another in the same time window, they might collide at some point. That can happen, but then is like any blockchain. Like the first one will be the one having succeed on the state transition. Then voters can override their vote privately. Also, this is a very important property for coercion resistance and so on. We allow the voter to, in any time during the voting process, to send again the vote. And in order to hide the overrides from votes, we are performing random re-encryptions on every state transition. So on every state transition, a sequencer must re-encrypt randomly a number of votes. And so an external observer or other sequencers do not know for sure if it's the user, a voter, that sends an override to the network, or if it's a random re-encryption from the sequencer. So this is how we are mitigating bribery and coercion. At the end, votes are decrypted and results are published. So the sequencers will need to also to exchange some information. This can be done. This time can be done off-chain in order to decrypt the results. It's important that in this process of decrypting results, the key for decrypting the results cannot be used for decrypting individual ballots, only the results. And then one of the sequencers or a coordinator of sequencers or whatever will create a ZK snark proof proving that the results are correctly decrypted, and will send this a new transaction to Ethereum. In this transaction, we mainly have the last state root, the results in plain text as a public inputs, and that's it. And then as a private input, we have some Merkle proofs and so on to prove that we are correctly decrypting the results. So the decryption of results matches with the encrypted results that is available inside the state tree with that root. So with this proof, we already have the results and we have the last state root. And now let's talk a bit more about how did we organize the circuits. There is a lot of ZK snark code in our implementation, and circuits is the main thing here. And so this is some decisions that we take for implementing the circuits. First, we're using Groth16 for now because it's cheap and easy to verify on Ethereum. But in the future, we might also go for Plonk or other variants. We're using Circommand SnarkJS on the client side. And in our experience, for ZK snarks, this is the best on browser and especially on mobile phone browsers, which are very limited. So if we have this real world, let's say, non-technological users around, we need to provide a solution that works for all of them. And to be honest, SnarkJS is the only thing that, in our experience, work everywhere. And that's thanks to Jordi Bailina and all the work that he did with programming in WebAssembly directly and optimizing everything. So it's amazing work. And this is something that we know we want to use in the client side. And in the backend side, at the end, we started trying SP1 and some ZK VMs, but it was heavy. It was maybe too heavy. And then we had the issue with decentralization, what I was telling before. So if we want something that can be running, let's say, almost commodity hardware, then we need a solution with do not require like a GPU or a cluster of GPUs and 1 terabyte of memory. So we end up using GNARC by consensus. It's a very fast and highly optimized prover. And especially, and this is why we decided to use GNARC for now, is that it supports many curves, but especially these two curves that allow native recursion. So as we are aggregating votes, then we need to have a good recursion framework, and these curves available on GNARC work pretty good on this sense. And then yes, it's also not as high level as a zkEVM, but still the GNARC syntax is easy to use, to understand, and to implement. So that's also one of the points of GNARC. And regarding the circuits, we don't have a single circuit that makes everything. We have split the work in four, actually five. There is the results circuit, which is not here, but in the process of validating and aggregating votes, we have four circuits. The valid, which is the one in the browser, then the authenticate, and also transforms the proof. So we have a BN254 proof from Circom in the browser. Then we change to the BLS curve here on GNARC on the sequencer side, and then we aggregate with a native recursion, 60 of them, and finally we create the state transition. This design, I think, is nice because the second circuit, the authenticate, can be parallelized. So you can have a cluster of devices doing the proving of this zk snark. So you can scale horizontally. Then you have the aggregate, which is a heavy task, but it's okay. And the state transition is also heavy, is the bigger circuit, but it's reduced to the minimum scope that we need for proving the state transition. So in case you have a collision with some other sequencer, you only need to repeat the last circuit, the state transition. This is the time and the number of constraints that everyone needs. They are not yet optimized. I think we just implemented them. Actually, we achieved a complete flow 2 weeks ago or something like that. But we are still in heavy development. So we believe that these numbers of constraints and so on will be reduced in the future, for sure. And at the end, I have added some estimation about what's the cost of a vote, because this is also a very important question to understand the sustainability of the whole system. And these are the numbers. So we're using right now this kind of server to create the proofs, which is an AMD Ryzen 9, that you can find it for $150 a month in some providers on the internet. And then as the votes are being added to the queue, and they are being processed one after the other, we can process a number of approximately 14,000 votes per day. So the whole calculation, also taking into account the gas cost of the transactions to update the state root on Ethereum, gives a number, that's an approximation, of course, of $0.0013 per vote, which is okay, I would say. Yeah. And finally, let's talk about the risks that we have detected. I mean, nothing is perfect. DAVINCI is not perfect, and there are some risks and some things that we need to improve probably in the future. And there are probably some new risks that we still don't know that will appear, because voting is very hard. It's a very hard problem to solve, to be honest. So yeah, sequencers can collude to decrypt individual votes. Good thing here is that they cannot manipulate results, since everything is zk snark proven, but they can break privacy. So the mitigation here is that if you need something that is very for high stake election that requires that the voter is anonymous forever, let's say, then you can use another cryptographic scheme on the identity of the voter. Instead of using Ethereum addresses, let's say, you must use ADDSA addresses. And then you can anonymize also the identity. on the first circuit generated on the browser, because you can generate a valid nullifier. Yeah, availability or censorship. So that can also happen, like sequencer go down for some reason, or they decide not to process a vote. The good thing here is that anyone can send a valid state transition. So if sequencers are not available anymore, you can even run your own sequencer. Sequencers might also collude in order to not decrypt the results. The mitigation that we have for that is to require a collateral and slice them. So yeah, if you want to be a sequencer that holds an encryption key, then you need to provide some collateral. And then also compromised voting devices means that, for instance, the mobile phone you're using for voting is compromised and it manipulates the vote at the last time before you're voting. This is a very hard complex to solve. But what we can say is to use verified UI frontends or devices. But of course, we consider that the web application or the mobile application that the user is using for voting is secure. Yeah, and finally, just saying that the testnet is almost here. I hope at the end of June we will have something already public on Sepolia, so people can start to play, to test the system, to participate as sequencer or keykeeper or something like this. So yeah, we are very open to create new collaborations and to have early adopters for our testnet. So yeah, you have the link here to a forum. You want to stay up to date about this upcoming event, and you can also scan the QR code. And that's it.
Thank you so much, Pau. Yeah, so while Pau was explaining like the technical part of DaVinci, thanks for putting your addresses here. I created a test voting process. So the idea is that anyone can test what we have been building. So right now, I will share here in the chat a link to the voting process. This is the UI we're using right now. Under the hood, it runs on the Tendermint custom layer 1 network. But the idea is that you can get an idea of how the voter or what the voter feels when it's using the application. I can go a bit later if we have time on the process of the creation of the election. But here you will experience the same experience that say a real world user will have. And yeah. Just a disclaimer, this voting is anonymous using Zcash snags, and the results will be published at the end of the session. So if you're using a mobile phone for voting, the computation on the client side is quite heavy. We try to maintain it as the minimum as possible. But if you're using like a mid-low-end mobile phone, take your time. Maybe it takes like 50 or 40 seconds to generate your vote envelope. So yeah. Let me share the screen so I can also show the voting from my side. Let me check if I can do that. Okay. Yeah, I think it's already pinned. Yeah, it's pinned. Perfect. So yeah, the idea is to vote on our favorite topic, which is pizza. So the idea is that we create an approval voting process to help the PSC group to collaboratively decide on the ideal combination of ingredients for our pizza. So here you have a list of toppings that that you can choose. So you can choose one or even more of them, and yeah, the idea is that also your role remains anonymous and with all the things that we explained, and you can also override your vote. So this is what the user will see at the end. So first, this is like my organization. I already have added my address and yours, of course. And first thing you need to do is to sign up. So first you sign here. I'm already signed in. So in that case, for example, if you want a two-factor authentication, when you sign up, you need to put like your credentials, and then there's a second step where you receive the two-factor authentication, and then you can vote. The cool thing about this is that this is created with Ethereum addresses, but it can be extrapolated also to private database that organizations can have, and so on. So that's why we need. I mean, we want to maintain the census creation very open, because when you face like real world organizations, they have different ways of managing their member base. So yeah, in that case, for example, my toppings would be tomato sauce, mozzarella, onions, bacon, and arugula, for example. Okay, now I just need to select, press on vote, and now my vote is being created on the client side. Because it's anonymous, it takes a bit for creating everything, but I think in some seconds we will see that the vote is already processed. And then what we give is a link to an explorer that we have, which is an explorer for the L1 network. And someone that doesn't know about technology can just click on a verify your vote button, and he or she can see all the information about their vote while remaining anonymous. So let's see, the presentation and the live presentation gods help us, and hopefully this will not break. Let's see. Okay, maybe meanwhile I can go. Yeah, okay, now my vote is submitted. So you can see like okay, this, I can go here to verify my vote. So I can press here, and this redirects me to the voting explorer. So I can see that my vote has been registered correctly. And here, this is the election I voted on. Here are the details of my vote. So for example, I didn't overwrite my vote. These are some encryption, the encryption key index that was used, and yeah, and some cryptographic information. And here we can see the vote package, which was encrypted, and it contains all the relevant information. So yeah, a user that wants to verify their vote, they can just use the code that you can see on the top, on the bottom left side of the screen, which is your identifier, or this one. And then you can just go here, verify your vote, and you add your vote ID, and this process your vote and says if your vote was tampered and it was or not, and it was correctly put it there. So yeah, now for example, I can resubmit my vote if I change my mind, or if I've been coerced because someone is pointing me with a gun saying that tomato sauce is not like the right option and we should put pineapple. And then I can change this vote in front of him or her, and then I can just resubmit my vote. And this was like the UI that the voter will see when voting. Okay, and yeah, just for not extend it like a bit, here I have my organization, and when creating a new vote, I can just go to a new voting. Here I put a title, description, the start time and end time. For example, tomorrow at 7 p.m. And here I can put, for example, I want the results to be encrypted until the end. I want to allow vote overwrite. I want the vote to be casted anonymously using the ZK Snarks technology. And for example, if I click next, here I can choose the voting type. So we have single choice, approval voting. I can put my question here, options, add more options, then click next. And here's, oh, sorry. And here we have the cool part, which is the census. So we support custom data, Gitcoin passport, Ethereum wallets, token based. Here, for example, you can select your network and import the token you want. And then we have, for example, integrations via phone number, email, CRMs, database, digital certificates. So cool thing about the custom data is that you can download a CSV template, and then you can put all the fields here that are recognized by the UI, but also on the at a protocol level for authenticating the user. And yeah, you just put your census here. For example, when I created this election, I was putting the addresses that you shared with me here, and I was adding the addresses one by one, or I can just upload a CSV. And then when I click next, the election basically is created, and you get exactly the link that I shared with you here in the chat. So that would be like the voting experience. And as I said, this for now is like a production environment and is being used by the organizations and by the people. And the idea is that once we have DaVinci production ready and everything is properly audited and so on, we just will do a swap and we'll use like the new backend. And also the UI is the organization management and so on is being revamped a bit, taking into account all that being years. So, yeah, that was the demo.
I think
yeah.
Jordi, I think we might end the voting. Have you created it?
Yeah,
like,
I think I can
because
do it.
there are 7 out of 8 votes. So
okay.
there is someone that has not cast a vote for some reason, but
yeah, maybe I can end the voting here. Okay. So now when I end the process, the backend will have a signal, and then the encryption keys will be published, and the votes could be decrypted, and we'll have the results. So I click on end process. So the transaction is being pumped. Okay, so the voting has ended, and hopefully you will see the results in a while. Let me refresh screen. Okay, so yeah, we have the results here. So if you go to Explorer also, I can go to processes. We created the collective pizza voting, which has ended. We have the published encryption keys, and here we can see the results on the Explorer too. Here and also on the application. So our perfect pizza would be pizza with tomato sauce, with mozzarella cheese, some onions, some pineapple also.
no.
And yeah, that would be like our perfect pizza for the PSC Learn and Share team today. So yeah, I hope
pineapple. I cannot buy that.
Well, it's just a matter of preferences. Okay, so I hope that you enjoyed like the live session, that you enjoyed the voting, and you had a great experience. And yeah, hopefully with the new system, we can optimize a bit more on the client side, so you don't need like to wait that many seconds. But we will see. So yeah, that's it. Any questions that you might have, please feel free to write it, and we'll be super happy to answer them. Thank you so much.
Great, thank you so much, guys. I think I'll start with a question, if you don't mind. So I wasn't sure about the state transition. So you mentioned that can be done by anyone, right? So you don't need to be a sequencer, or you do. Like I think you mentioned about the stake being needed, but yeah. And also I wasn't really sure about the sort of race condition, because if you can like in parallel like provide state transition, and if someone does it before me, then technically mine would be outdated because I would be starting from an old state root. So how does that work?
We actually are splitting the work of keykeepers with the sequencers. So in the beginning, we had everything together, like a sequencer will hold a key and so on, as a slice of the key. But in the last months, we have decided to split. So because this is more censorship resistant, as anyone can send a state transition. So there is no actual point for not allowing anyone to send a state transition. So in one side, we will have the keykeepers. You can run a sequencer, which is also a keykeeper, or you can just run a keykeeper, or you can just run a sequencer. And for running a keykeeper, it will require very low profile hardware. So you can use maybe a Raspberry Pi, whatever. You only need to hold the key. So we also expect to have more distribution on the key if we do this way. So and the key keeper is the one that requires to provide some collateral and so on, not the sequencer. The sequencer will get paid because of the work they doing. So depending on the number of votes that you have sequenced, then you will have a share of the budget for the voting process. But it's not he's not going to be slashed.
And what about the race condition part? So when you submit the state update, like, is there some sort of like start and stop where only one can do it at a time, or how would that work?
Yeah, we still don't have this problem. So I like to see like a lot of sequencers and votes going on. Then we can think about that. But my first take would be to try to build something off chain, some communication channel, maybe through IPFS, using Gossip Poop or whatever kind of protocol, in order to let the good behavior sequencers at least to exchange information about, hey, I'm doing this transition, so others can just try to coordinate a bit. But yeah, let's say that we will allow some competence here too. So if you have a data race, you need to rebuild your state transition and send it again.
Yeah, and another thing that we thought about, it was to provide like a time frame for the sequencers to be able to upload the state transition. So let's say if the sequencer public key ends in an odd or even number, for example, you will have like this time frame for that you are allowed to submit a state transition. But we still need to figure this out, like with a real case scenario and doing some simulations.
Nice. And what about the census? Like, where is that stored? So, like, is my understanding that they use it that never actually talks with Ethereum, right? They just like send the proof and everything to you, to the sequencer, right? And yeah, like, how would someone verify the census? And
Yeah, the census, it's out of the scope of the protocol. It's more in the application level. So it's another layer. And yeah, we want to provide tools in order to build censuses and to verify censuses on chain. But yeah, in our experience, most of our experience is on Web 2. So usually the organizations have a census some way. You can audit the census. So at some point you can see, you can verify that if you have a member base of 10 people, you have 10 keys on the census, for instance, and you can also randomly ask to the people, this is your key. No, so that's something that can be done. And in the other side, if you want to build some census out of Ethereum information, then the way would be to either to use some optimistic approach. So we have this tool with this service that we call Census3, which scans the Ethereum network and will build a Merkle tree of the census out of any token that you want. But then you need to post the census root somewhere and to wait for someone to challenge it or whatever. So that's an optimistic approach. And the other is the ZK approach, which means that you can build the census and then you can create a ZK snark proving that the census is correctly built using the storage proofs. This is feasible, at least with the technologies that we have been exploring, to up to 1,000 or maybe 10,000 addresses on the census. Then maybe with commodity hardware, you need like few hours in order to create this snark to verify the census, which is feasible.
great, thank you. I think we got a few in the Q&A as well.
Can we see somehow?
Yeah, if you go next to the chat, we'll have this square made of points. You can go to questions and answers.
Oh, great.
And if you go to view, I think Vivian was the first, if I'm not wrong.
Okay. So the first one is why SMT and not AMT. I think AMT means indexed Merkle tree. So we go for a sparse because I mean, proving a state transition is not easy because you need to prove a lot of things. Yeah, you need to prove that you have changed some value, some path or some leaf, and then you must also prove that you have not modified any other leaf on the tree. That's hard to achieve. It's a hard problem to achieve. So with indexed Merkle trees, yeah, they are smaller and so on. They are more efficient, but we didn't find any existing implementation that work for us with all the requirements that we have. And for the sparse Merkle tree, we have the ident3 implementation from Circom that we have port to GNARC, and it contains exactly what we needed. So this sparse Merkle tree and the processor implemented with Circom is exactly to prove this kind of state transitions. So for now, we're using an SMT. But yeah, maybe in the future we change to even to Merkle trees or whatever else.
Okay. Next one is, have you compared your solution with other similar projects addressing the same problem?
Yes, we have. I mean, I don't want to go into details. Every solution is a valid solution and it covers probably different needs. We have learned a lot from Macy, for instance. Also from conversations about how to improve Macy. I think our solution and ZK Macy are quite similar in some aspects. But yeah, I think we maybe are more focused to scalability, and Macy or ZK Macy is more focused to on-chain voting. But that's just a take. I don't know in deep all the details. Then there are other solutions similar. We have Helios and Velayos and so on, which are also systems that achieve similar properties without using ZKS NARCs, but they are not decentralized as far as I understand. And there is always a kind of authority or single point of failure. Yeah, and in terms of decentralized voting and open source, I think DAVINCI and Macy are probably the only ones, at least the ones that I can find. You take the next one, Jordi.
Yeah. So how are sequences incentivized to behave honestly? This is via token. Sequences needs to stake some tokens in order to be able to get sliced if they don't behave properly, and then the organizer of the elections need to pay upfront those tokens, and the cost of the election is calculated via a formula that we have described on the paper, and then depending on the number of rewrites, the votes processed, and so on, the final cost of the election is calculated, and the sequencers keep the economic incentive for the votes that they processed and so on, and then the organizer will get back like the difference. And the other part of the question is, what is the economic security slicing conditions required to keep the sequencers behaving honestly? So right now, we didn't have a lot of time to make proper calculations on that. We didn't have a lot of time to make, let's say, some prospections on the cost that we'll have. But the cool thing about this is that the way that we envision this is that the organizers will have the free will to choose how many sequencers they want to use. So they can tweak a bit like the security level. So for example, if you want to use all the sequencers of the network, you should be paying to all the sequencers of the network, and then the election will be more expensive. But yeah, this is something that we need to finally figure out. We have like the basis, and yeah, we need some more time to work on the details of this.
Yeah. Well, the next one is a clarification, and IMT means incremental Merkle tree. I think the same answer applies. Actually, an indexed Merkle tree is also incremental. So yeah, nothing else to comment here. And Dennis O'Neill is asking about a way to connect for a user, for a voter to know on which proposals can he participate. Yes, this is out of the DAVINCI protocol scope, but this is in at the application level. And as we are working on this new application, actually, that the one that Jordi showed is, let's say, the old one, but we are cooking a new one, which will be very nice and much powerful, I would say. And on this new web application, we will support things like that. Yeah, because that's also a need that we detected from some other use cases.
Yeah, so I think we are done with the questions. Yeah, I just wanted to point out like some things. Is that I think there's like not a lot of people in the world working on digital voting, and I'm always trying to push for collaboration and to try to build something together. I don't know if this should be like the World Voting DAO or something like that, but I think it would be nice like to exchange information about what we are building, the way we are trying to solve these problems, and so on. So 2 weeks ago, we had the call with SIP.org voting, and I had the pleasure to exchange some information with the founder. And it was super nice because, I mean, we kind of ended up trying to solve like the same problem from the UI perspectives and so on. And given that we are like not that much people, and yeah, and this thing is difficult, and especially at a social layer, also for politicians to adopt the technology and so on, I think we should be pulling together and trying to upgrade the way we are voting, because yeah, paper voting is is not that much nice nowadays. So yeah, we are open also to contributions on the code. If you have some feedback on the paper, please reach to us. If you need further clarifications, reach us. I think we can share here our contacts in the chat. Also, if you need the slides, please feel free. I don't know, Alex, if they will be updated, like uploaded, sorry, on the YouTube channel. But if you need so, we can send a copy, so yeah, people can follow the slides too. And yeah, just wanted to say thank you to the VSC team for having us here today and to give us the opportunity to present the things that we have been cooking over the past years. And yeah, hopefully we'll end up having like a proper solution that solves the needs.
Thank you.
Yeah, thank you so much, guys. This was awesome. Yeah, you know, there's a bright future with all the stuff that you guys are building, Civ is building, Macy, Enclave as well. Like, it's good that people target it in different ways. And, you know, I want to be optimistic, and, you know, I really like your energy and everything. I think you guys are doing great work. And yeah, it was a pleasure to have you. Yeah, if no one else has got any questions, you know, sorry, go on, Bob. Yeah.
You
No?
wanted to say something, Paul?
No, sorry.
Oh, okay,
Okay.
fair enough.
Sure.
No worries.
Okay. Thank you, everyone.
Yeah.
Cool. Thanks.
Yeah, I know. Yeah, I wanted to say that thank you for organizing this event. I think it's amazing what you're doing here.
Cool. Thank you for coming. Yeah.
Really appreciate it.
Awesome. I'll stop the recording.